welcome back. Just a quick message before we begin. You find the weekly schedule if you just go to the basic GitHub address, and if you look into the README file and you go to the bottom there, you will find also the link to the video. And it takes some time to produce a subtitle. So the link which you have, the one which I upload immediately, doesn't have subtitles. But then, if you just wait a little bit, it takes roughly, since the video is pretty long, it's up to 2 hours. It uses sometimes it uses more than 20 hours to produce the subtitles. And probably there's quite some queue of many people doing that. Okay, so the links which you see here, I mean, from last week, they should also contain subtitles. You find the lecture to the lecture material which I'm covering, and you also find typically some reading assignments. And this textbook by Sabo and Oslund covers pretty well some of the basic things which we are dealing with now in the beginning. The other thing is also that you find the same information here. If you look at the schedule and you scroll down, you will see that we upload the same information about what are the plans for the week, and you will also find the links to the videos of the lectures. So in case you are not able to be here, you can always look back at the video. So I'm going to move back to the whiteboard and try to finalize these calculations which we looked at yesterday about matrix elements, which lead to something which are called the Condon-Slater rules. And then we are going to move into second quantization, and that's going to keep us busy for the rest of the semester. So let's bring up the whiteboard so we can do that. And let me just bring that one up. Okay, so yesterday we were looking at the calculation of an expectation value of a one-body and a two-body operator. And we concluded more or less the calculations with a one-body operator. So the thing I wanted to do now is to go through a general two-body operator which keeps the permutation and translation symmetry. So the typical one-body operators which we have seen as a one-body operator, one of the examples. So when I put a 1 there, it's to indicate that this is actually a one-body operator, this subscript 1 here. And examples which we have been looking at has been this operator H0, which contains the sum of the kinetic energies and typically the external potential which the particle is confined to move in. So for the two-body case, we have examples there which we discussed as this H1 here, which then is a sum over, so it's a double sum over the interaction matrix or the interaction operator. And this is normally a function of the relative distance between the particles. And in the exercises which you've seen this week, we make this kind of assumption that this symmetry is actually contained in the specific operator we're looking at. And many of the operators you end up looking at in physics, they do actually have similar symmetries. So we can easily assume that that is the case. Now, what we did yesterday was to look at the case where we had n equal to 4. So I'm just trying to wrap up this discussion. And we looked at the calculation when you had a state on the Ket side which differ by one single particle state from the state on the brass side. And we made a notation there. So for this specific case, we were looking at a transition probability between a one-body operator, which we did yesterday, and then we were looking at a two-body operator, and then we had a Slater determinant here, which we marked in this specific case with an alpha 3. So there was a state which we had specified to be different from the one in the Slater determinant on the brass side. And we had an alpha 3 marked here. So this is a kind of notation which you will see in the literature, which indicates that when we are looking at such transition probabilities, there is a difference between the two Slater determinants. The other alternative which we could have is something like a phi of O2 here, and then we can have two different single particle states. So let's look at these two cases. So we could now have alpha 3 and alpha 4. and then we have an alpha 3 primed and an alpha 4 primed. So let's look at the first case. And it's useful to write out the matrix elements in terms of integrals. So if we take this case, what we would have then, and now we are looking at we are plugging in the operators as well. So we would have an integral dx1, dx2, dx3, and dx4. And then we had a single particle wave function 1 for x1, alpha 2, x2, psi, alpha 3, complex conjugate, x3. This is multiplied with an alpha 4 of x4 here. And then we have the matrix elements, which we have now to plug in. So we would have V, and then we have x12 plus V of x13 plus V of x14, and then we get plus V of x23 plus, so there will be 6 matrix elements in this particular case. And note that the sum is defined so that we don't have any double counting. And this contains then x of 24, and finally we have a V of x34. So these will be the matrix elements, or the interaction elements which we need to evaluate. And this is again multiplied with the Slater determinant, or actually the wave function with permutations. So we have this specific permutation operator, P, and then we have minus 1 to the power of P, and then we have this operator acting on this state which now contains alpha 1, x1, phi alpha 2, x2, and now I have a phi alpha 3 prime, so it's not the same. And then I have an alpha 4 of x4. And then I have to do the permutation. So keep in mind that the permutations, this is the sum of all possible permutations. So if you have a typical determinant, you can permute pairs, but you would also have the permutations of 3 objects, 4 objects, and so on. Okay, so if we look at the first term, I mean from this one, so this is going to contain 1, and then it's going to be a minus P12, minus a P13, etc., where we have done all the permutations. And we see that the first term is a term which only, when we now look at V12, if we take this first term here, what would you expect that gives us? Yeah, that will be 0. So if you look at this specific term here, that will actually give us 0. And the reason for that is that this specific element has now a phi alpha 3, which you see here, which links with phi alpha 3 here. And then, since this is a normalized states, it means that this integral, since it's not acted by the interaction, then the norm of that specific contribution has to result in 0 because the states are different. If I take alpha 4 and alpha 4, that's no problem, but it's alpha 3 prime and alpha 3 which causes a problem. So that means that the term which now contains Vx12, we can actually leave that one out. If you now think of the term which has x14, what would you expect from that one? The same. So we can leave that one out. If I take the term x24, that would give us the same. So we can leave these terms out. And what you notice now is that what is going to give a contribution will actually be the interaction elements which involve one of the other particles with that explicit particle which has changed the single particle state. So that means that the elements which you see here, this element, that will give a contribution because it will now contain this alpha 3 prime and alpha 3, and we don't know whether the matrix, when we calculate the integrals, whether this is going to be 0 or not. So that means that we cannot set it to 0 before we actually have checked whether it could happen that it is 0. So this is a likely contribution. It means that this will also be a likely contribution, and it means that this is also going to be a likely contribution. And then if we look at the contributions from the different permutations, what we will end up with is a contribution which looks like as follows. So this is going to be equal to a sum. So we will have a sum here over the states alpha I, but with alpha I different from this alpha 3 prime and alpha 3. So we're going to have matrix elements which are going to look like alpha I, and then I'm going to have alpha 3 here of V, and then I'm going to have alpha I of alpha 3 prime, and then I will have the matrix elements which comes due to the Pauli principle and which we call the exchange matrix elements, and that is going to be given by an alpha I alpha 3 of V of alpha 3 prime of alpha I, like this. So remember now that when we looked at the so-called contribution from the, or what we call the expectation value yesterday, when we had the same Slater determinant on the Brown and Ketz side, then we had a double sum over all the single particle states. And now we just end up with a single sum. So this means that if you need, when we are setting up now a Hamiltonian matrix, and if you look at exercise number 2 this week, that contains the basics of a method which is called full configuration interaction. And when you do a full configuration interaction, you're actually computing these different matrix elements in the computational basis. In our case, the computational basis is this set of many-body wave functions, which are eigenstates of this operator H0. So next week, I'm actually going to go through this exercise 2, which we had today, because that contains many of these basic features of a many-body problem, and where you will typically see that if you increase the strength for the interaction, that means you make this part more dominant, then you will depart from a state which is mainly dominated by one or two of the computational basis states. So if you then need to calculate matrix elements for the computation of a Hamiltonian matrix, as you did in this exercise number 2 for this week, then you need to compute matrix elements like that. And then when you compare the Bra and the Ketz side, you can easily find out whether they differ by 0, 1, or 2 single particle states. If they differ by 0, then you have an analytical expression, and the only thing you need to plug in are the matrix elements, this table. If they differ by 1, you have the same thing. You have this analytical expression you have to calculate. And if they now differ by 2, so let's look at that case. So the next situation we are going to look at now is the same matrix element, but now we are going to look at the state phi, and then we have this hi. Let's look at that specific operator, hi. Let's specialize to that, because that's often what we're going to calculate in the beginning. We're just going to look at the energies. But now we are going to assume that there are 2 single particle states which are different. And then we do an alpha 4. So we have specified those which are different, like this. And this matrix element is going to be proportional with, again, the same integral dx1, dx2, and dx4. Sorry, dx3 and dx4. This is multiplied with phi alpha 1. This is going to be one of the last times when we write out everything in all details here, because when we move to second quantization, life is going to be a little bit simpler. This is then multiplied with, and then we put up the matrix elements. So we have the interaction contributions, not the matrix elements, the interaction contributions. So we have these 6 terms, x14 plus v, x23 plus v, x24, and the final one, which is v of x34, like this. And then we have the permutations. So we have the sum over all the possible permutations of the permutation operator, and then we multiply with phi alpha 1, x1, then we have a phi alpha 2, and then we x2, and we have a phi alpha 3 prime, x3, and multiply with the final term, which is a phi alpha 4 prime, x4. I can see the excitement here. Okay, so the what we end up with then, if you now start looking at terms, suppose now we pick the vx12 term. If we now look at that one, what would you expect from that term? If we now just take this one. 0. What about x13? Also 0, because now we have this guy here, which teams up with this one, and we are calculating norm of that, so that's 0. And this follows, this is also 0. This becomes 0. This becomes 0. And the only matrix element which is not 0 is, or tentatively not 0, is actually the one which involves the 2 single particle states which we have changed. So that means that this one becomes simply equal to 1 term. And this is going to be given by alpha 3, and so this will contain alpha 3, alpha 4, v alpha 3 prime, alpha 4 prime, minus, and then I have alpha 3, alpha 4 of v of alpha 4 prime, and alpha 3 prime. Now, if I were to give you, instead of an interaction which acts on 2 particles at a time, what would happen here if I had an interaction which acts on 3 particles at a time? So this is just a small question here, and you can, so suppose now instead of this v, we have a v which acts on x, 1, 2, 3. So all these v's now are replaced by an interaction which is of a type of 3-particle interaction, or normally what we call a free body operator. So could you, without running any calculation, could you see what that should become? That should be 0. So if you have a interaction here, which is of the type of a free body interaction, and you have, no, sorry, actually I have to give you one more thing here. So if I now have no, sorry, it's just me messing up here. It actually wanted to ask another question before we begin with that. So suppose now that I change the Slater determinants, and I have a Slater determinant where I now have 3 single particles which differ. What would you get then?
You should get only the term, only 1 term, right? I don't think it would be 0.
Now, if you have states, because the interaction now acts on 2 particles at a time.
Oh, was still okay. I was thinking
Yeah.
about the
Yeah,
interaction.
I was just,
And with three
yeah,
different.
yeah. So if you have a two-body interaction, this is if you differ by more than two single particle states on the Brown and Ketz side, that is automatically zero. So that means that we can set up, if you now have phi here and an interaction of a two-body type, and then you have an alpha 2 prime, alpha 3 prime, and alpha 4 prime, and then you have an alpha 2 here, alpha 3, and alpha 4. This is automatically zero if V is a two-body interaction.
Because you could never get two permutations which
Yeah.
wouldn't contain two.
Exactly, exactly. But if I have a three-body interaction, it doesn't need to be zero. So this is something which simplifies the calculation. So if you then compare two Slater determinants or two determinants, and you see that they differ by more than two single particle states, and you have a two-body interaction, you can automatically set that contribution to zero. And typically, as I mentioned yesterday, the way you would encode this information about the determinants is to take these and rewrite them in terms of bit strings. So a state which is occupied has bit 1, a state which is unoccupied has bit 0. And then you will simply compare bit strings. And if they differ by more than 2 bits, then you don't need to do anything. So that's a very easy way to set up a Hamiltonian matrix when you have a complicated many-particle state. Now, this kind of exercise here is a little bit clumsy when you do this in terms of first quantization. So I did this also to motivate for the introduction of second quantization. So let's move on to second quantization formalism. And let's look at how we can compactify everything. But before we do that, we need to introduce some calculation rules and some definitions. So the way you can think of now, when we look at this single particle states which we have defined, so let's set up second quantization. Or what I normally like to call number representation. This is also called Fock space. So that means that you define a new Hilbert space where you've taken out the spatial degrees of freedom. Now, if you look at the single particle states which we had, we have a certain number here. So we have an alpha 1, alpha 2, alpha 3, and then these go up to some cutoff which we define. We can also define states which are filled up to a certain level, and that would define what's normally called the Fermi level. But we could now say that we have a certain limit here, and that limit could be an alpha of n here. So that's the final single particle states which we have. Now these can be translated into boxes, so you could actually think of having a box here which now points to quantum numbers. So if we are in a typical atomic physics calculation type, then these quantum numbers could point to n1, the number of nodes the wave function has. It could point to the orbital momentum. It could point to the projection of the orbital momentum. It could contain spin of the particles and so on. All the quantum numbers which are needed to define that single particle state. So this would be a slot for alpha 1. We would have a slot for alpha 2, alpha 3, and then you can place particles in these different slots. So you can have 0 particles or you can have 1 particle there. So just to remind you, so n here, it should be n. Just to remind you of this, we have now chosen an ordering, and that ordering is going to define the way we define state functions. This is the same way as we did with the Slater determinant in what we normally call in a sloppy way first quantization, where we also included the spatial degrees of freedom. And then we chose an ordering of the single particle states. And a typical ordering is one where you have a chosen basis, and then you order them according to the single particle energies. Because then you would often infer that if the basis you make, the many-body basis, based on the single particle basis, the energies which you get then, if the interaction is weak, that will be a dominating contribution to the total energy. So it makes a meaningful physical approximation to the systems which we are looking at. Now, what you quickly see then is that you could think of having a particle here, you could have a particle here, and that means that you would have a slot here with bit 1, bit 0, bit 1, and so on. And in total, we would now typically have n particles. And since these are fermions, it means that every slot is occupied by at most one particle. That's a consequence of the Pauli principle. That means that the total number of configurations, so I'm just writing configs, is now going to be equal to this binomial factor, which is n, the number of slots which we have, and the number of particles. And we've always assumed that n is smaller or equal than n here. So this tells you quickly how easily the dimensionality can grow, because in principle, this n, this single particle basis, has an infinite set of single particle states. If you just think of the harmonic oscillator, you have an infinity of bound states in a harmonic oscillator potential. Okay, now what we are going to define now is a set of operators which are going to create particles in a given state and destroy particles in a given state. So the first thing we're going to define now is a vacuum state. So in that state, there are no particles. So we define a vacuum state, and we're going to label that one as 0. So that means in second quantization that there are no particles in that state. So second quantization is also referred to as a number representation, because you're looking at the number of particles which occupy each slot. And you will see then that the matrix elements which we are going to need, or the transition probabilities, these are elements which then can be tabulated, and the only thing you are going to use then are the indices here, these ones, and with these indices you're going to look up in a table and you're going to fetch matrix elements which can be pre-calculated, or you can calculate them on the fly if you have an analytical expression. And in many cases, you would choose a single particle basis where you can even get analytical expressions for the matrix elements, so you can calculate them on the fly, or they can be evaluated numerically easily, and at the same time, they are physically meaningful. So that's the ideal when you pick a basis here. So we would define such a vacuum state, and then we are going to define a one-body operator, which is called a creation operator. And this creation operator is something which we're going to define like an A, and it's going to refer to one of these quantum numbers which we have. And I'm just going to write it like alpha here. And it's given with this sign here. And this acts on the state 0. And then it creates a particle in a state alpha. And this is going to be written like this, alpha here. So these are just notations which I'm going to introduce. So that means that we now have created a state which has one particle in the slot with quantum numbers pointed by this number alpha. Okay? So these are just definitions here. So if I now look at the two-body state, so this is a one-body state, I can now define a two-body state. And what becomes important now is actually the ordering. So this is a two-body state. And this is going to be given by, and now we're going to distinguish a little bit, because we're going to have an alpha 1, dagger, and then an alpha 2 here. And this acts on this state 0. And you remember the compact notation which we introduced last week. We had a notation for the state, which was given in terms of these indices alpha 1 and alpha 2. So these are actually tens of products when we now want to fetch the specific state function. So you can think of this as a kind of abstract representation of a given state. And where you now have made a transformation from your standard Hilbert space with all the quantum numbers to a Hilbert space which excludes the spatial degrees of freedom. But you would fetch the spatial degrees of freedom by just pointing to these specific quantum numbers. Okay, so now so this implies a specific ordering. We also want these states to be anti-symmetrized. So if this is now going to represent our Slater determinant, so that means that the Slater determinant, or the determinant which we set up before, is now given by this representation alpha 1, alpha 2 for the two particle case. If I have a many particle case, for many, it's going to be given by an A alpha 1 dagger, A alpha 2 dagger, and then I'm going to go up to A alpha n dagger. So I have n particles, and this acts on 0. And we can rewrite this one in terms of I equal 1 up to n, the number of particles we have. And then we have an A alpha I, so there's an alpha I here, dagger acting on 0. Now, when you look at this definition which we haven't baked in any properties about the Pauli principle. Now, since we are dealing with a single particle basis, the consequence of the Pauli principles is that you cannot have more than one particle in a state. So we have now to define a rule here. So for this to represent a Slater determinant in this new space, which is normally called Fock space, we need to have the implementation of the Slater determinant. So which means that I have to have A alpha 1 dagger, A alpha 2. So let's restrict ourselves to the two particle case acting on 0. So this has to be the same as minus A when I interchange particle 1s and particle 2 here. So this is the way we are going to bake in the anti-symmetry. So a general Slater determinant is going to be represented in this way. So this is a state with n particles, which now fill these different slots. It does not need to be the lowest lying state in this computational basis, but it could be any Slater determinant. In this specific case, since we have filled up all the states up to alpha n, it could represent the ansatz for the ground state of the system. So in this specific case, what we have is this operation here, but we need more. We need also now to have, so if I have a state with alpha 1, which is the same as A alpha 1 acting on the vacuum state, what I need to have now is that A alpha 1 dagger, if I now try to put in another particle in the same state, I should get 0, right? So this would also apply to this alpha 2. If I have already a state alpha 2 which is occupied, if I try to put in another particle, that has to give me 0. Now you can see then if you combine this relation here, so if you now take this relation and you simply just rewrite it, so the definition which we have put in, so if I just rewrite A alpha 1 dagger, A alpha 2 dagger, and I just shift over to the right-hand side, this term which you have on the left-hand side, the term which you have on the right-hand side, I get plus A alpha 2 dagger, A alpha 1 dagger acting on 0, and that is equal to 0. And then, since you also have the fact that you cannot occupy the same state, what this leads to is a anti-commutation rule. So this leads to the first anti-commutation rule, which simply says that if I have A alpha 1 and A alpha 2 dagger, this is going to be equal to 0. So this is the way we implement one part of the anti-symmetry. Okay? So the next thing which we need is to define what's called a creation operator, an annihilation operator, after we've done the creation operator. So we would now define the next element, so-called annihilation or creation operators. And in that case, this is simply the Hermitian conjugate of the creation operator. So this is the Hermitian conjugate of A dagger. So that means that I'm going to have an operator A, which is simply this operator A dagger and the Hermitian conjugate of that one. Now, this is going to have some calculation rules which we need to define. And one of the calculation rules which we are going to define is that A acting on the vacuum state is equal to 0, obviously. I mean, there's nothing to destroy. And then, no, sorry. I actually wrote creation here, that's wrong. So this should be destruction. Destruction sounds a little bit more, I would say, violent than annihilation. So I normally use annihilation.
I think it's the other way around.
Yeah, yeah. Sometimes destruction sounds like, I don't know. I mean, to me, it sounds a little bit more violent. Yeah. Okay, so this is one of the calculational rules which we need. Now, the other rule which we need is that if I have a state now, which is, and now I'm going to put the quantum numbers on here to indicate that this is acting on a specific state alpha. So if this state is occupied, what we are saying here is that we have an A alpha, and then there's an A alpha dagger acting on 0. So this is going to annihilate a particle from the vacuum state, and that brings us back to the vacuum state. So that's another rule which we need to have. Now, when we look at that one, and then we think of the anti-symmetry here, it's easy then to take this anti-commutation rule which we have for the creation operators and simply replace that one with a similar anti-commutation rule for the annihilation operator. So what we're going to get then is a new commutation rule. So we would have an A alpha 1, A alpha 2 here, which is also going to be equal to 0. So the way you can read this, if you have a state with n particles, acting on it with the annihilation operator creates a new Slater determinant with the n minus 1 particles. So if we have a general state, if we have, suppose now a state which contains alpha 1, alpha 2, up to some alpha n here, then if this alpha is within this alpha 1, alpha 2, up to alpha n. So this is something which we will call an n particle state, because we have filled the slots with n particles. Now, if we have an n particle state, and if now this alpha is contained inside here, then what we would have is that we have an A alpha acting on A alpha 1, A alpha 2 here, and then we move up to some alpha of k, and then there is a state which is actually equal to this alpha, and then we have an, sorry, let me just rewrite it. So I would have an A, and then I would have an alpha K dagger, and then I have this A alpha dagger here. And then I'm going to have a state A alpha K plus 1. And this goes all the way to an A alpha of n, acting on 0. Now, there's one thing which I haven't told you yet, because there's another anti-commutation rule which we're going to define after the break. But this state here is going to now remove a particle in the state alpha. So this will remove a particle in the state alpha. So that leads to an n-1 particle state. So it means if I now take the norm between this state, so if I take the norm between alpha 1, alpha 2, up to alpha n, and where I have this state alpha in here, this A alpha, and then I have an A alpha 1, alpha 2, and in here there's an alpha, and this moves up to alpha n. The action here is going to produce an n-1 determinant. Here you would have an n particle state, and so this overlap has to be equal to 0, because they would represent states with different numbers of particles. Now, if this state alpha is not contained in the set of alpha 1, alpha 2, up to alpha n, then clearly you're just acting on a true vacuum and you're trying to destroy a state which doesn't exist. And that would give you 0. So then we would obtain 0. Then A alpha acting on this state, alpha 1, alpha 2, etc., up to alpha n, is equal to 0. Now, the thing we need now, in order to be able to make calculations, we need another rule, and that's the rule for creation and annihilation operators. So we need that. So we have two anti-commutation rules. So one is this one. And then we have this one. But we need one which involves a creation and an annihilation operator. So let's try to look at that and just derive that rule. So let's quickly set up the definitions which we have. So we need now to look at what happens when we are acting with the state on a state which has n particles with an operator which goes like A alpha dagger A alpha. We need also to look at the case where we have different states. So it could be something like this. We also need to look at what happens when we have A alpha dagger, and also when we have A beta and A alpha dagger like this. So after the break, we are going to look at the cases when these different combinations act on a many-body state. And there will be different possibilities. So if I have alpha and beta, then alpha and beta can be contained. One of them can be contained, or both of them can be contained. And then we're just going to set up the cases, and based on that, we are going to be able to deduce an anti-commutation rule, which goes like A alpha, A beta, dagger, which is equal to delta alpha beta. But we're going to derive that one after the break when we look at the different outcomes of these operations on a given state. And then you will see that this is the final rule which we're going to need. And with these three rules, we can now start to calculate the transition probabilities and expectation values in a very compact form. However, what we are going to get is not as compact and efficient as desired. And that motivates the introduction of something which is called Wick's theorem, which is a very, very useful theorem, which allows us actually to evaluate expectation values and transition probabilities in an extremely efficient and simple way. So I'm going to put the recording on pause now. So the thing we're going to look at now are the final commutation rules. And in order to do that, let's now look first at the case where we operate with this operator on a given state. And then we're going to look at this case here. And then we're going to take the general case. So let's take a small look at the case where we now have a given state. And we have an A alpha dagger, an A alpha. And this is going now to act on a state where we have an alpha n, alpha 1, up to an alpha of n here. And the assumption now is that this alpha is not included in this set of states, alpha 1, alpha 2, up to alpha n. Now, if that is the case, it means that we are trying to annihilate something which does not exist there. So this is a pretty obvious case, so that has to be equal to 0. So let's look at the next case now. So we can now look at A alpha on A alpha dagger, and this is now acting on the same state here, alpha 1, alpha 2, up to alpha n. Now we have to make some basic assumptions. So we can now assume that alpha is again not included in alpha 1, alpha 2, up to alpha n. Now, one of the things we have to be, when we write this state now, this is, we can now place this alpha as this alpha, and then we get a new state, which has an alpha here. And then we have alpha 1, so we haven't changed the order of the creation operators here. So that means that we had a state with the slots 1, 2, up to n being filled, and then we just add a particle in that slot, but we don't care about the ordering we have chosen for the single particle states. So this could actually be 10 here, slot 10, and then we have slots 1, 2, 3, up to n. However, what you see here is that when this is not included, this obviously has to be different from 0, because if alpha is included there, then it would be 0, because we cannot have two single particle states with, two particles in a single particle state. So this means that when we then act on this alpha again and destroy it, then we are just back to the state alpha 1, alpha 2, up to alpha n here. So that's okay. So let's see now what happens if the state is contained. So let's now assume that alpha is actually included in this alpha 1, alpha 2, up to alpha n. So the case when it was not included was trivial. So let's look at that case. And what we are going to take now is an A alpha dagger, A alpha, and this is going to act on this state, alpha 1, alpha 2, up to alpha n. And now we have to be a little bit careful when we are setting up things. So the state which we have, so we have an A alpha, and now we are going to have an alpha 1, alpha 2, and then there is an alpha k, A, and then we have an alpha here, and then we have an alpha k plus 1, and then we end up with the alpha n here. So in between here, there's a state alpha. Now, what we want now is that this state which you have here, this alpha, which actually has an operator, A alpha dagger, this obviously acts only on particle alpha. What we want now is to move it, because every single state here, keep in mind the notation which we have, is the tensor product of a Hilbert space. So when you are looking at this state which we put up here, this is alpha 1 tensor product with alpha 2, and then finally the tensor product with alpha n. So when I'm now acting with such an operator, A alpha, I want to have this in the right place in this ordering which I've chosen. So I want actually to bring this operator, which you see here, I want it to bring over here so that it stays together with A alpha acting on its own one-body Hilbert space. So I'm acting with this one on that. So in order to be able to perform that operation, since this is actually a tensor product, it's a compact notation, I now want to have A alpha acting on that one, and I don't want to have any of the other operators in between. So I need now to use the rule which we had before. So A alpha dagger, A beta dagger is equal to 0. So that means that A alpha, A beta dagger is equal to minus A beta dagger, A alpha dagger. So what I need now is to flip this operator here, and I need to move it over here.
Where are the here's?
Say again?
I couldn't see where you were pointing.
So what I want, I'm just going to rewrite it. So I'm going to have an A alpha here. And now I'm writing out the full wave function in terms of, or the state in terms of the creation operators. And then in here, there is an A alpha K. And now I have my A alpha here. And then I have my A alpha K plus 1, etc. And this is acting on 0. So what I want now is actually to bring this to here, so that I can now insert 0 here, and then take the action of the operator A dagger alpha on that state. It creates a state alpha, and then this one destroys a state alpha. So in order to get this kind of ordering, so that these operators are together and act on their specific Hilbert space, because I actually ended up with an ordering here. So what I do then is simply to use this anti-commutation rule, and every time I change it, I get a minus sign. So that means that I can rewrite this state as an A alpha dagger, A alpha, and then I have a minus 1 over K. This is the number of slots I've been moving it due to the anti-commutation rule. And then I get an A alpha dagger, and then I have an A alpha 1, and then I have an A alpha K dagger, A alpha K plus 1 dagger, and then this continues to an A alpha N dagger of 0. So this is now going to give me a new state. When I look at this, that this is going to have an A alpha dagger multiplied with minus K, and then I have alpha 1, alpha 2, alpha K plus 1 up to alpha N. This is now a state which you see here is an N minus 1 particle state. So now this slot is gone, alpha, so that means I can create a particle in alpha. And if I do that, then what I get now is minus K, and then I have alpha 1, alpha 2, up to alpha N here. But then I want this alpha back in the slot where it was. And to bring that back again, what I'm going to do then is to just reuse this anti-commutation rule. And that gives me minus K, minus 1 to the power of K, and have it twice, so that's plus. So this brings me back to alpha 1, alpha 2, alpha K, alpha K plus 1, and up to alpha N. So far so good, right? On the other hand, if I now take A alpha A alpha dagger and act on this state, and alpha is contained in this state, then what would we expect then? That's zero, right? We cannot put two particles in the same slot. So if I now take these two terms, which I have, so I have this one. So if I take now and shuffle over to the right-hand side, so what I would get then is that I have if I take these two terms, let me just cancel that one. What you see now is if I act with A alpha dagger plus A alpha and A alpha on this state, where alpha is contained in the state, what we get then is just alpha back to the same state. So the first one, this one is zero, and the other one just brings me back to the state. So what I would have then is simply that if I have A alpha, I can rewrite it like this, A alpha dagger, which is the same as A alpha and this is equal to 1. Now, remember now that when you set up these commutators or anti-commutators, this is actually an operator acting on something. It's always a little bit sloppy notation because what this implies when you set this equal to 1, it means that it's actually acting on some kind of state. Now, the next thing we need to do now is actually to look at A alpha dagger and A beta, and then we need to look at A beta, A alpha. And the exercise is basically the same. So we will have going to have a state alpha 1, alpha 2, up to alpha n, and we will have three cases. Alpha beta not contained in alpha 1, alpha 2, up to alpha n. The next case is obviously alpha and beta both contained in alpha 1, alpha 2, up to alpha n. And finally, we have a case where one of them is contained. So alpha or beta are contained in alpha 1 and alpha n. So in the lecture notes, you can actually see this kind of what this is going to lead to. So I'm just going to summarize it because it's not so exciting. It's just a repetition of what we did here. And I wanted more to go into applications as soon as possible. So what this is going to lead to, when you repeat the same exercise as we did with alpha equal to beta, what you end up with is the anti-commutation rule of A alpha dagger of A beta, which is given by A alpha dagger A beta plus A beta A alpha dagger equal to delta alpha beta. So these are the commutation rules which we have. So if we summarize now, or anti-commutation rule, which is more correct. So if we summarize, what we have is a creation operator, A alpha, acting on the true vacuum state. And that is something which we would write like this. So this is a single particle state now. Because we assume now that these creation operators are operators which act on a one particle state. So we would call this a one body operator. Then we have a alpha dagger acting on alpha. This is equal to 0. We have A alpha acting on the vacuum state, which is equal to 0. We have A alpha acting on the state alpha, which brings back the vacuum state. Later, we can always, the nice thing with second quantization is that you can always redefine the vacuum state. And later we are going to see a vacuum state which is redefined according to where you have defined the Fermi level. And that's going to simplify calculations further. And then we have the anti-commutation rules. So we have an A alpha, A beta is equal to A alpha dagger, A beta dagger equal to 0. And the final commutation rule is an A alpha dagger, A beta. You can interchange these two actually. And that's equal to delta alpha beta. So these are the basic calculational rules when we are dealing with second quantization. So let's look at examples, because that's always useful. So let's take example 1 here. And in this particular case, we are going to look at a two-body Slater determinant. So we have a state, which I'm going to define as an alpha 1, alpha 2 here. And that's going to be given by A alpha 1 dagger, A alpha 2 dagger acting on the vacuum state. So this is my ansatz for the for given state. And now I want to calculate the norm of this state here. So what we want to do now is simply to calculate an alpha 1 prime, an alpha 2 prime, and then alpha 1 and alpha 2 like this. So instead of writing the Slater determinants, which we did before, we are now going to use second quantization. And we are making an assumption here that these states are normalized and orthogonal. So that means that if I take alpha beta here, this is actually given by delta alpha beta. And you can see that in second quantization, this means the following. So it's going to be A beta acting on 0. And then I have A alpha, the complex conjugate, which acts on 0. So this is the way you would write this norm, which we normally have written in terms of an integral. This is the way you would write the single particle norm in second quantization. And you see now you create a particle in state beta, and then you want to destroy it. And in order for that one to be different from 0, alpha has to be equal to beta. On the other hand, if I look at another element, which is given by A beta dagger, A alpha 0, what does that give us? 0, exactly. So this is by definition 0. And this is going to give us a kind of driving rule here when we are calculating transition probabilities and expectation values. So the whole machinery we are going to look at now is to place all the creation operators to the left, and then we do the annihilation and destruction operators to the right. That sounds almost like a political statement. Destruction to the right and creation to the left. Sorry. Some people from the right wouldn't agree with that. Okay, but you see, these two equations here, they are going to show us how we can now actually calculate such a quantity. Now, when you're going to see me doing these operations now with the anti-commutation rules, you will see that this is not very efficient. And this led Giancarlo Wick to actually develop something which is called Wick's theorem, which allows us to calculate this without the boring thing which I'm going to put you to sleep now with. So let's just write this out and use the anti-commutation rules. So what Wick's theorem is a way, in an overarching way, to find out which of these terms are 0 and which are not, instead of you just going in a slavish manner through all the possible permutations. So keep in mind now that when you look at the So the simple case with just a one-body operator is very straightforward. But when we take this term now, this is going to look like as follows. So we have a 0, and then I'm going to have an A alpha 2 prime. This is the complex conjugate, so Hermitian conjugate, and then alpha 1 like this. And then I'm going to have an A alpha 1 dagger, A alpha 2 dagger. So if I...
Just a silly question. Have we stated that the complex conjugate of the creation is the structure?
Yeah, that was a definition we put in the beginning. Yeah. So we actually, if we go back a little bit, so this becomes important also if you want to introduce time, because that will change a little bit the definitions here. But what we did was actually to, so this was the creation operator. And then when we went down a little bit here, we defined also the annihilation operator here. So let me just go down to the bottom here. And now you see what you would do now, based on this formula here, is that you would like to have one of these annihilations operators to the right. So if you're able to do that, then we can immediately set that term equal to 0. So if you now take the anti-commutation rules, you can then shuffle around these operators. So let's see how we can do that. And now I'm just going to leave out the zeros, and I'm just going to look at the operators themselves. So what I could do now is to interchange alpha 1 prime and alpha 1. So I would then keep it like this. And now I'm using the anti-commutation rule. So there's a Kronecker delta minus A alpha 1 dagger, and then A alpha 1 prime. And this is then multiplied with A alpha 2 dagger, like this. So it is enough to have one annihilation operator acting on the vacuum state. So what I could do next now is simply to take this term and anti-commute it with that one. And then I know that in this specific state, alpha 1 prime has to be equal to alpha 2 as well. That's the only possibility which we have. So what happens then is the following. So I would keep this one, I keep this alpha 2 prime, and then I get an A alpha 2 dagger, and then I get a delta alpha 1 prime, alpha 1, and then I have minus, and let's rewrite this one. I have an A alpha 2 prime, A alpha 1 dagger, but then I'm going to anti-commute this next guy here. So I'm going to have a delta alpha 1 prime, alpha 2 here, minus an A alpha 2 prime times an A alpha, no, alpha 1 prime, like this. So what I did now is simply to take this guy here and anti-commute it with that one. So I get a Kronecker delta, and then I have rewritten this operator in terms of that. So in this particular case, what we are going to get then is that when this acts on the vacuum state, I have an A alpha 1 prime, which then is trying to destroy something which doesn't exist. So the last term here, I'm just going to wipe it out. The last term here becomes 0, so we can just leave it out. Now, if I look at the first term which I have, so let's go back to that one. So let's rewrite a little bit now. So now I'm going to take the A alpha prime, A alpha 2 prime with A alpha 2 dagger here, and I'm going to anti-commute that one. So that's going to give me a delta alpha 2 prime, alpha 2 here, minus an A alpha 2 dagger, A alpha 2 prime. And this final term here, these terms actually multiply with alpha 1 prime with the Kronecker delta here. And now we see that the last term here is actually equal to 0, right? Because this is a state or this is an operator which now acts on the vacuum state, and it tries to destroy a state which doesn't exist. So we can put a cross over this one. Let me just use the red one just to cross them out like this. Then the next thing we will do then is to look at the term which we have here. So we will get a minus. And now we have a Kronecker delta of alpha 1 of alpha 2 prime minus. And then I have an A alpha 2 prime. No, sorry, alpha 1 dagger. And this is again multiplied with delta of alpha 1 prime of alpha 2 here. Then what we have is now a term where you see now quickly that this final piece, this alpha 2 dagger, when that acts on the vacuum state, this gives us 0. So the what we end up with then is 2 Kronecker deltas. So we would have a delta alpha 2 prime, alpha 2, multiplied with a delta alpha 1 of alpha 1. And this contains now minus a delta alpha 1 of alpha 2 prime times a delta alpha 1 prime of alpha 2. And this is what you would have if you have a state where the Slater determinants may be different. If now you specify to alpha 2 is equal to alpha 2 prime, and alpha 1 has to be equal to alpha 1 prime, then clearly the last Kronecker delta doesn't apply. Because then we are just simply saying that alpha 2 has to be different from alpha 1, because we cannot have the same particles in the same slots. So that means that if this is the case, if we are calculating the norm of alpha 1, alpha 2, of alpha 1, alpha 2, like this, then you see now that this is actually equal to delta alpha 1, alpha 1, and delta alpha 2 here. So this is just a way to demonstrate that we are getting the norm correctly in second quantization. However, what you see here, and if you think of this in terms of the calculation with a Slater determinant, this doesn't look very impressive, because we have to run through all these anti-commutation rules. And this is where Wick's theorem, which we are going to look at next week, comes in, and is going to make this calculation much, much easier. So right now, I mean, you have to forgive me a little bit, because it doesn't look like as if we have introduced a compact notation, but it doesn't seem like we've gotten any type of gain from just writing out the integrals and just writing out the Slater determinant for 2 particles. And if we get more than 3 particles here, it's going to get pretty clumsy. So let's look at a new example. And now I'm going to define an operator. And this operator is going to be defined in terms of A alpha times A alpha. A alpha dagger times A alpha. And what I'm going to do now is to make a sum over all the particles which are in the system. So I'm going to define an operator with a hat here, which is normally called the number operator. And this operator is going to be defined as a sum over alpha equal 1 up to the number of particles which we have. So this is going to be an A alpha dagger, A alpha. Now this operator has some specific properties. This operator has some specific properties here. So let's look at the given state. So we have a state now, which we define as an alpha 1, alpha 2, up to some alpha n here. So that's the state we are looking at. And this specific state Of course, if alpha is not contained in here, then we would have alpha 1, alpha 2, up to alpha n. Then clearly, if I'm acting with this operator on this specific state, alpha 1, alpha 2, alpha n, the answer should be obvious, right? It's not contained there, so we're trying to act on the vacuum state and create and actually destroy something which doesn't exist. So this one has to be equal to 0. So if all the alphas contained in that operator exist, so if I have now alpha is contained in the operator alpha 1, alpha 2, etc., up to alpha n, then the situation is going to be a little bit better. So if I now compute these quantities, if you now remember that if I have A alpha acting on this state, alpha 1, alpha 2, up to alpha n, this gives us, when we do the computation, if now we have a state alpha k here and an alpha here, we need to make these permutations with the anti-commutation rules. So we will get minus 2 to the power of k multiplied with alpha 1, alpha 2, up to alpha n. If you go back to what we did when we derived the anti-commutation rule. So that means that for every single of these, this just produces the state again. And since we are summing n times over that, what you will see then is that when this operator n acts on this state, alpha 1, alpha 2, up to alpha n, this is simply the number of particles multiplied with alpha 1, alpha 2, up to alpha n. So this is called the number operator, which has as a quantum number the number of particles. And that's a useful quantity because that often in many of the many-body methods, you want to conserve the number of particles. And there are many-body approximations where you don't conserve the number of particles. So this is a very important operator to actually calculate in order to check that you're running things correctly. So that was one example. The next example, and next week we're actually going to derive the second quantized version of an operator. But let's now look at the operator H0, which we defined to be, in first quantization, to be the kinetic energy divided by 2m, then we can have an H bar plus an external potential. This depends on x. Now, this was the operator in first quantization. In next week, we're going to derive the expression for the operator in second quantization. Now I'm just going to give you the expression. So the general operator in second quantization, this is going to look like a sum over alpha and beta. It's going to have a creation operator A alpha, annihilation operator beta, and then there's going to be a matrix element, alpha, H0 times beta, and this element which you see here, and now we have not assumed that this is a diagonal basis in H0. So this matrix element is the same as an integral d of x of phi alpha complex conjugate of x H0 multiplied with phi beta of x. So that's the compact notation. And normally we choose a basis which is diagonal in this H0, but this would be the general definition. And now we can go back to this operator which we looked at, and suppose now we want to calculate the expectation value of a Slater determinant where we have an alpha 1, alpha 2, a two-body Slater determinant, and then we have an alpha 1 here and alpha 2. So this is an expectation value. And we are going to make life a little bit simpler. So we are simply going to assume that this one is actually given by delta alpha beta times the single particle energies. So this makes life a little bit simpler. So that means that the operator now, alpha beta of A alpha dagger, A beta of alpha H0 beta, that simply reduces to a sum over alpha, A alpha dagger, A alpha, multiplied with epsilon alpha. Now the thing now which you see if you go back to this number operator, because we did parts of the calculation already here, but we have to be a little bit more careful. So the thing we need to evaluate now, when we calculate this expectation value, we need to evaluate a term which goes like alpha 1, alpha 2. We have an A alpha 2, A alpha 1. So we're calculating an expectation value now. And then we need to set up this sum. So we have a sum over alpha, and we have an epsilon alpha, which I'm just leaving out like this. And then I have an A alpha dagger, A alpha, acting on A alpha 1 dagger, A alpha 2 dagger of alpha 1. No, sorry, this is not correct. This is the vacuum state, and this is the vacuum state, like this. Now here, we can take immediately what we did for the number operator. So if you look at this operator here, there's a sum over alpha. So it would act on alpha 1 first, and then on alpha 2. So that should simply give me the number of particles in that specific state. So we could actually take this one, A alpha, dagger, A alpha, acting on this state alpha 1, alpha 2. So what we know then is that this, if we follow the number operator which we put up here, then we know that this is similar to the number operator, except that we have a constant epsilon alpha here. So when this acts on that state here, what we have then is that we are going to get epsilon alpha 1 plus epsilon alpha 2 multiplied with the state alpha 1 and alpha 2. If I had the number operator, I would just have 1 plus 1. And at the end, I would have 2 particles. But now, since I have this term here, I need to keep track of that one. And then what I need then to multiply with is actually the state alpha 1, alpha 2. So this is simply going to be epsilon alpha 1 plus epsilon alpha 2. Now I'm going to leave you with a small exercise. So instead of thinking of the number operator, which simply gives us now the number of particles in the system, try to use the anti-commutation rules and go through the calculation of these quantities with the anti-commutation rules. You will get tons of these Kronecker deltas. It's going to be pretty boring, but you will get the same result. So I'm bringing this up to motivate the introduction of Wick's theorem. Because if you want to run through these calculations with the anti-commutation relations, you're just going to get lost, because somewhere you're going to write some indices wrongly. You can automatize it, but this is what Wick's theorem does. And that's what we're going to discuss next week in more detail.